So this is the part 2 of chapter 1, and this is a section 1.1.2, which covers extrinsic semiconductors. And extrinsic semiconductors are it's where you have a material like silicon and you've doped it or added in impurity atoms. So it's some pure material or some material that's been doped with impurity atoms, and that makes an extrinsic semiconductor, or the same thing would be called a doped semiconductor. And by doping it, you can increase the number of holes. So doping increases, whoops, the number of holes, or the number of electrons. And you want to dope it because that pure intrinsic silicon has a low number of charge carriers, since the only thermally generated holes or electrons are available. And so that gives you a very low current handling capabilities. And also doping modifies the conductivity / resistivity of the material. And so usually you would dope silicon with a group 3 elements to add holes. And in the book, they basically just cover the use of boron, which is a group 3 element, to add holes. And then group 5 elements, I should say, add electrons to your material. And the book covers mostly phosphorus, but they also mention arsenic as a group 5 element. So again, if we start out with this group 5 dopant, phosphorus, and we have a lattice with phosphorus in it, whoops, and we can draw, I'm not drawing everything, I'm just sort of drawing around the phosphorus atom. And it's going to have 5 valence electrons. So it has one other electron right here. And this electron can easily move into the conduction band. Did it again. So that unpaired, unbonded electron on phosphorus can move into the conduction band, where it's free to move around. So I'm talking about this one right here. And so if we draw out the molecule again, or not molecule, but the crystal lattice, a piece of it. And again, it goes on basically forever. And where these would be other silicons. If that electron moved into the conduction band, now this phosphorus would have a positive charge on it, and then we'd have some free electron kind of floating around in the conduction band, okay? And this phosphorus ion and this positive charge can't move. Can't move. It's stuck there. So it's not free to move around at all. And we call this phosphorus ion. The phosphorus is a donor impurity because it's donating an electron and that can move in the conduction band. And now our semiconductor is considered an N-type semiconductor when it's been doped with phosphorus. And overall for this area, the number of electrons is now much, much greater than the number of intrinsic holes. We talked about intrinsic last time. It was the number of holes and electrons that are generated just by thermal equilibrium. And we can calculate the formal charge on the phosphorus simply by using that formal charge is equal to the number of valence electrons in the atom minus the unbound electrons, minus 1/2 the bonded electrons, so bonded electrons, we'll call it BE. And so for in this situation, before that electron is moved, the valence electrons for phosphorus is 5, and then it has one unbound electron and minus 1/2 the number of bonded electrons. So there's 1, 2, 3, 4, 5, 6, 7, 8, because each dash represents 2 electrons, so 8. And so this equals 0, so no formal charge. But in this situation, where the formal charge is equal to 5 minus, there's no unbonded electrons, and then 1/2 the 8, it's going to give you a +1. So that's where you get the plus right there on phosphorus. And the most important thing on this whole slide, like I said, is this phosphorus that's now sort of an ion with a positive charge on it can't move. It can't move around. And so this doesn't contribute any current. This free electron does. So that's the group 5, and the other one was the group, whoops, let me undo that. The other one was the group 3 dopants, and what they use is boron. And if you look at boron, it's 1s2, 2s2, 2p1, because it's boron 5. And so it has 3 valence electrons. 3 valence electrons. Or you'd write it like this as an isolated atom. 1, 2, and 3. And so again, if we draw out some silicon lattice that has been doped with boron, now we have this boron atom that's been inserted into the lattice. And now some electron from a neighboring bond can move in there. And we can draw it now as a BSI and so now this has a negative charge on it. And then we have generated a hole. So this is a hole that can freely move. But we've generated no electrons. And so we've only made holes. And again, we could calculate the formal charge on the phosphorus. In the first case here, we have the formal charge is equal to the number of valence electrons minus the number of electrons that aren't involved in a bond minus 1/2 of the 6, which is going to equal 0. And then in the second case, just to point out that this electron belongs to silicon and not to boron, so that's why this is 0. And then in the other case here, we have again 3 in the isolated atom minus the 0 of non-bonded electrons minus 1/2 of what's in a bond, what's in the bonds, and there's 8 electrons in the 4 bonds, so that's going to give you minus 1 overall. So that's where you get the minus 1 formal charge on the boron that's shown in the figures. So boron is an acceptor impurity. And because it's accepting an electron. And as I said before, no electrons are created in this when you dope with boron, and so you generate a lot of holes. And once you have a piece of silicon doped with boron, it now becomes a p-type semiconductor. And so just to repeat again, an extrinsic semiconductor is intrinsic semiconductor is the same thing as a doped semiconductor. And both of these just mean that it has added impurity atoms. Now, the book presents this relationship. And again, as in most things in the book, they don't derive these relationships, they just state them. And someone once told me that these were all just, you'd have to take some type of physics type class where they derive or maybe empirically derive these things. But the relationship is the number of electrons at equilibrium times the number of holes at equilibrium is equal to the intrinsic concentration. Remember that intrinsic one was like bt to the 3 divided by 2 e to the minus eg over 2kt. And that was basically your number of holes and electrons that were generated in a pure substance at a given temperature. And so the number of holes times the number of electrons at equilibrium is equal to the intrinsic concentration squared. And just to remember again, a donor gives electrons, and an acceptor accepts electrons. So this was your phosphorus doped, and this was your boron doped, because the boron accepted an electron and then became positive, and this donated an electron and became, negative, and this one became positive. And if you have a donor, and so this is like the concentration of your donor atoms, if it is much, much greater than your intrinsic concentration for that temperature, then since the donor gives an electron, your number of electrons is going to be approximately equal to your number of donors. And therefore, if you use this equation up there, then your holes at that temperature equilibrium will be equal to Ni squared over the concentration of your donor, okay? And likewise, if your number of acceptors, and so that's your phosphorus type semiconductor, as much as greater than your intrinsic, so your dopant concentration here of your boron, then your hole concentration is approximately equal to your number of acceptors. And so your number of electrons for a p-type semiconductor at equilibrium is going to be equal to the intrinsic concentration squared divided by the number of acceptors. So this is your boron dopant concentration. So I'll say boron dopant concentration, and this would be your phosphorus dopant concentration. And some last terminology. So if you have say an N-type semiconductor, N-type, so that has a donor atom, which is phosphorus, added to your silicon, then electrons are your majority carrier. And then the holes is your minority carrier. So this should be not majority carrier. Okay? And for a p-type, then it would be opposite, where the holes would be the majority carrier and the electrons would be the minority carrier. And so we'll just work at the end of that section, there is example 1.2, where they say calculate your number of electrons at equilibrium or the number of holes at equilibrium for, and then it's a silicon at 300 Kelvin that's been doped with phosphorus, so that, and phosphorus is a donor, so that's Nd is equal to 10 to the 16th per cubic centimeter. So that's the concentration of your phosphorus atoms per cubic centimeter. And previously we calculated that Ni is 1.5 times 10 to the 10 per cubic centimeter. That's your intrinsic concentration for silicon. And so we just say that your number of electrons at equilibrium is approximately equal to the number of donor atoms, which is equal to 10 to the 16th per cubic centimeter. That was given. And again, that's if Nd is much, much greater than Ni, which it is. Ni is 10 to the 6th, and this is 10 to the 16th. So this is your NO concentration. And then PO is just going to be Ni squared over Nd, which we just stated. So that's going to be 1.5 times 10 to the 10 over 10 to the 16th. And this is all squared up on the top. And so this gives you 2.25 times 10 to the 4th per cubic centimeter. So you can see in a N-type semiconductor that's been doped with phosphorus that the electron concentration is much, much greater than the hole concentration. And then in part B, they say for silicon at T equals 300 K again, and it's been doped with boron, so that, and boron is an acceptor, so Na is equal to 5 times 10 to the 16th per cubic centimeter. So now we have a high concentration of boron, so PO, that's your number of holes, is approximately equal to Na, which is equal to 5 times 10 to the 16th per cubic centimeter. And then we just, and again, that's if Na is much, much greater than the intrinsic, which it is. It's 10 to the 16th for Na and 10 to the 10 for your Ni. And then we can calculate the number of electrons, which is going to be Ni squared over Na, which is equal to 1.5 times 10 to the 10, all of this squared, over the 5 times 10 to the 16th. And this comes out to be 4.5 times 10 to the 3 cubic per cubic centimeter. So again, for a P-type semiconductor that's been doped, silicon doped with boron, your number of holes is 5 times 10 to the 16th that was given. It's much, much greater than your number of electrons, which is only like 4,500. So that concludes this section.